Okay. Well, thank you very much for having me. And I enjoyed hearing Professor Kajita's talk in Japanese. I understood every 10th word, okay? Now, I don't know how well you will do with my English, but let's see, maybe once every 15th word, I don't know. Anyway, let me start by pretty much the same place where Dr. Kajita quit. This is a picture he showed also, but and I think later in the questioning, when we have back and forth discussion, we will talk a little more about what is a gravitational wave. So I want to talk mostly about some new results that have come from the whole network of gravitational wave detectors, which you see here. These are the two American ones, one in Hanford, Washington, and another one in Louisiana. And they were the ones that made the original detection. But very quickly thereafter, there was a detector in Pisa, Italy, which is a 3-kilometer detector. These are 4-kilometer detectors, which joined. There's always been a research detector run by the German and the Scots in Germany. And now, of course, we have CAGRA, which you heard about, which is doing some very new things, very elegant new ideas are being tried in CAGRA. In particular, trying to build it in a mountain so you are not troubled by certain classes of what we call geophysical noise. And also the idea that you use low temperatures. That's the thing that none of these other detectors are doing. They're low temperatures to keep the mirrors cold so that you have less thermal noise. That's a big, very important experiment that's going on in this. And now there's another detector being built currently in India, which is very much like LIGO. Anyway, these detectors, here are the ones, what they look like in the United States. This is a quick little tour of what they look like. This is the one in Louisiana, and I will start a little movie so you can see what they look like. This is the one in Pacific Northwest, and these are the tubes in which the vacuum system laser beams go back and forth. Same thing in Louisiana as it was in Washington State. Here's that tube, very much like what you saw in CAGRA. And here is where people's working on making the laser work. And this looks very much like a laboratory and a university. And here is the room in which people control the detector. And these people are learning how to run the detector. So very quick tour of what LIGO looks like. I'm sure CAGRA looks the same when you get down at that level. Now here's I'm now going to talk mostly about what has been discovered. And very shortly after LIGO's advanced detector was turned on, we saw this. And this is a time series, time, and this is strain. Now, a gravitational wave asserts a strain. A strain is a ratio of a change in separation between the mirrors, let's say, of the ends at the detector, divided by their separation. So it's a change in distance divided by a distance. That is the field quantity in a gravitational wave. And so here you can see the scale of it. It's 10 to the minus 21. And we have a 4-kilometer long detector. So we're looking at things where the position of the mirrors are moving by only 10 to the minus 18 meters, which is 1,000th the size of a nucleus of an atom. And that took a long time to get right. But here are the signals that were seen very shortly after the advanced detector was going. And this is junk. Not interesting. It becomes more interesting as you go along in time, and then it gets really quite large. And that's the signal we saw in one of the detectors, the one in the south, in the Livingston. At the same time, we looked at the other detector. Here's junk again. This is noise, but again, something comes out of the noise. And this is there. We can put these two together. And you can see that they're not the same identically because of the noise, but the big parts of the signal are not so different. And in here, they're very much the same. This is, again, noise. So this was really the very first detection of a gravitational wave by man, a direct detection. There had been prior detections by inference from a pulsar system, and we can discuss that later in the questions if you get interested. And now I want to show you a little more about the signal. The signal can be you can present the signal another way. You can present it in terms of the frequencies that are, this is a Fourier representation. This is again time along this axis. And now we are not talking about, this is now frequency of the signal. So here, for example, is the middle C on a piano, 256 hertz. And you can see the two things in this picture at Hanford. Here's that same signal as a function of time. But here now is the way, the brighter this is, the more of that particular frequency is in the signal. So for example, this very bright section in here is all up in the region of around 200 hertz. And here's exactly the same kind of thing at the other detector. And the reason why I want you to learn about this is because you begin to get some instinct about what these gravitational waves sound like. And I'll play one for you. I don't know if you could hear that, but that is like that little blip at the end is a chirp. And now we can make it a little easier to hear by changing the frequency. That is a chirp. And now what is that? And what we think it is, and we are pretty sure of, is something that is just as important as the detector. What you're about to see now is a computer animation. This is not a drawing by an artist. This is the output of a computer solving Einstein's equations for the collision of two black holes. And we'll see that in a minute as I make this move. But down here is the waveform, again, that we were seeing in the pictures. We only saw this little bit of it at the very end here. And here is the time of the collision. And this now, I will turn it on, and I hope you will see what's going on. This is a rendition done by numerical solutions of Einstein's equations. And it took almost as long to get those programs working as making the detector work. It's a real triumph that this was done. So let me, as you'll see the two black holes, there they are. They're going around each other. And what you will see now is a surface of the geometry of space and time. And these little arrows show the stresses in space, and the colors show the time. For example, where it's green, clocks keep pretty good time. Where it's red, clocks have slowed down. And where it gets black, clocks have stopped completely. And now watch what happens as these get closer and closer. The space itself distorts. This is a two-dimensional version of the space. And the space itself, which was moderately Euclidean, becomes completely distorted. It becomes like an ocean wave. And now, for example, you can look into where the potential here is, for example, the time has stopped completely. And as these two holes get closer and closer together, they eventually form, and this gets slowed down so that you can see it, they form a new black hole. The two black holes have merged and they make a new black hole. And here's the radiation that's leaving it, which is what we detected. And this is a real triumph because you need, in order to do this kind of thing, you have to, when these two were colliding with each other, they were moving at about 0.6 the velocity of light. In other words, they collided at almost the velocity of light. And they are, here is sort of what we know about it. What they are here's again, a plot of time this way and strain this way. And this is what we've just seen. We just experienced this particular gravitational wave. That's the one we were looking at. And the parameters of that are quite remarkable. One of the masses is 36 times the mass of the sun. Another one's about 29 masses of the sun. And about 3 masses of sun disappeared into gravitational radiation. That is an enormous amount of energy that went off. 3 times the mass of the sun went off in about 1/10 of a second. During that little bit of time, that particular gravitational event was brighter than the whole universe by about 100 times. It's really enormous amount of energy that's associated with the gravitational waves, but they do so little. And that's a very important part of this whole story. It's a very, very hard thing for nature to distort nature. It doesn't want to, space does not want to get distorted. It takes a huge amount of energy to do that, and then you only get a little tiny amount of distortion. So anybody who talks to you about making gravitational wave communication is a little bit crazy, okay? They're very crazy, in fact. So here then is the first one of these saw. We didn't really believe this right away. And this tells you that this gravitational wave came on September 14th in 2015. Well, we saw another one we were not so sure of a little bit later. This was in October 12th of the same year. We were not sure of this one. But then comes Christmas time in the United States. It's Christmas. Anyway, about in the September 26th, we saw this. And that's a very different, it's still two black holes, one with 14 solar masses, another one with 7 solar masses. They're much smaller than these. And they only took away 1 solar mass of energy. And this is a very different waveform. It lasts a lot longer. And by the time we got to this, we began to believe. For a long time, we didn't believe this. We thought this was probably man-made, or somebody was hacking the system, as they say in the United States, or somebody was messing around, making trouble. But no, in the end, we began to believe that this was right. And the very important thing that happened a little bit later, in about 2017, is that not only was LIGO seeing these black holes, but also Virgo was seeing it. And that was a very, very important step in the whole idea of detecting gravitational waves, because now you had a way of doing something which we couldn't do before. I'll show you what that was. If you make a map of the sky, here's a map of the sky, and you take the 2 detections by the LIGO detectors, and the way you determine, for example, where a source is, that very first one we talked about, that came from the south. We saw it in Louisiana first, and then 7 milliseconds later, we saw it in the Pacific Northwest. That told us the source was in the south. It also told us right away that gravitational waves move very fast. We have a better indication of that in a minute. But right away, we already knew that the gravitational waves were moving close to the velocity of light. And they go right through the Earth. The Earth didn't bother them at all. So here is the best we could do with those timing signals here on this one. If you just use the 2 American detectors, you would get an uncertainty banana on the sky that's quite large. It's about 1,000 square degrees. And you tell an astronomer, go look there and see if you see something, they will laugh at you. They can't do that. That's too big a region of uncertainty in the sky. But adding Virgo to it, as now when Kagra is now going, would even make this better. You can do something like this. By putting the additional detector of Virgo, you can now make the area of this much, much smaller. It's about 30 square degrees, still bigger than the moon, but that's a little bit better. So this plays a very important role in the next thing we detected. We'll get to that. But here is sort of the summary of all the black holes that we have seen up to about a year ago. We have more that have not yet been published. But this is the mass of the black hole on the vertical axis. And this is just nothing. This is just a time if you want to think about it. Here are all the black holes that people in astronomy had seen by X-ray astronomy. And they're small, 1 to 2 solar masses, maybe, yeah. I mean, then, these are neutron stars, excuse me. The black holes that were seen by X-ray are the small ones in here, which are around 5 to 10 solar masses. And all the ones that are paired like that, where 2 of them had collected, those were all seen by gravitational wave. And now we have seen black holes that are as large as sort of 80 and 80 and 80, making something like 160 solar masses. And now it's getting very interesting. We don't exactly understand where all these black holes come from. And that's a big piece of new astronomy. How are they formed? We can talk about that later when in the questions also. But it's something that isn't completely understood. They could come from star collision. They could come from collisions in globular clusters. They might even be primordial. Well, there are very many different ideas about where they come from. Now, here's one of the most interesting things we saw. This was also in 2017. What this is, now that you know a little about what these signals look like, here is what the sonogram looks like for that signal. First of all, this is much longer in time. Here, from here to there is about 10 seconds. And here is the signal, which you'll hear in a minute. It's a signal that makes a very clean, chirpy sound. So let me play it for you. It's very low frequency until you get to the end. That chirp was something that we had thought about before, even when we were thinking about these detectors in the beginning. we were thinking we might see something like this, which you'll see in a minute, is two neutron stars colliding. But the very important thing associated with this detector is what is up here. This was not only detected by gravitational waves, the collision comes somewhere a little above this. We couldn't quite hear that because our detectors are not sensitive enough at the high frequencies. But it comes just about where that line is in time. So remember, this is time. And now here are signals that come from a satellite, the Fermi satellite, which is the gamma ray observatory. And here are two different energies of gamma rays, 10 to 50 keV and 50 to 300 keV. And they were seen something like 2 seconds later than the actual collision with the black holes. Now, and here it is. The best signal of all is this one right here. It's really very large. And this is another satellite that also was flying at the same time. It's not a very good signal, but it's pretty good. So now here comes some interesting things. Right from this picture already, you'll learn something really quite dramatic. What you'll learn is that these are electromagnetic signals. Gamma rays are electromagnetic signals. The fact that I haven't told you this, but I'm going to tell you, these two neutron stars are about 140 million light years away from the Earth. 140 million light years away. So the gravity wave signal, which is the signal that made this, and the gamma ray signal that have made that, have been traveling together for 140 million years. They're traveling all that time for 140 million years. And even if they are different in time by 2 seconds only, which probably isn't true, because it probably took 2 seconds for the explosion that the neutron star made to make gamma rays, but let's forget about that. Even if you count in that 2 seconds, it turns out that these two signals have been traveling so long together, you can say that a gravitational wave has the same speed as an electromagnetic wave to a part in 10 to the minus 15. So Einstein, when he first thought of this, guessed at that, but it's more than a guess now. It's a real good fact. So that's immediately something you learn from this. The other thing, which is very important that happened, and now because it was seen by not only, here is again this kind of sky picture, how well could LIGO alone see where this was? It's the banana here, that banana, the big one, and then there's another one down in here. But by adding Virgo to it, and with Virgo, it was a non-detection. It's a very long, interesting story, but there happens to be a zone of quiet where these detectors do not. There's a cone that's 45 degrees. That if you take the normal to the plane of the detector, and there are 45 degrees as a cone. And if the signal comes in that cone, it's very much less sensitive in that cone. And we now know that it was in that cone. By adding that in, and the Virgo was on and working, but didn't see it, it inferred that it was in that 45-degree cone. That reduced the signal to this size. And this is the uncertainty on the sky from the Fermi satellite. So this was very important. And because this was so small now, people who had telescopes could look at this themselves if we told them to go look in this region of the sky. And they did that. And what they found is they found a galaxy. Here's the galaxy. And here are stars that are in our own galaxy, but this is a distant galaxy. And this little new dot right there, where my pointer is right now, was not there 20 days before. Here's the same picture 20 days before this event, and here are the same stars. All of that's the same, but there's nothing right there. Well, that was very, very exciting for the astronomers, because now they had something to play with, and almost 30 or 40 different telescopes. In fact, I think it's more than that. It's probably 100 telescopes, all that lived in the southern hemisphere, went and looked at that, and they discovered really some wonderful things. And here's some of the things they discovered. Well, first of all, what was it? Here's a picture of what was the event. The event was two neutron stars. These are stars that are the mass of the sun and about the size of any city. It's a size, a very, very highly dense material that is sort of 10 to the 15 grams per centimeter cubed. And they were colliding with each other. They collided with each other. And while before they collided, there was a big mess of nuclear material here. All mostly neutrons, some protons, but mostly neutrons. And then it eventually made itself into a black hole. And what the optical display was made by the cloud of neutrons and protons. And it made something called a kilonova. And that was observed for something like almost several months. But it was and it had changed its color over and over again. And later on, the jets that flew out were measured by X-ray astronomy and also radio astronomy. So this was a fantastic experiment of all different astronomies working together. And this is called now multi-messenger astronomy. This was a big deal. And so here are some of the things that came out of that. Well, this is an interesting picture. You probably know this from high school. This is the periodic table of the elements. But it's written in an interesting way. You can see the source of the element. They're color-coded. And here, for example, things you know. Here's hydrogen over here. And way over here is helium. And you'll notice they're blue. And blue means they came out of the explosion that made the universe. They existed from the very earliest moments of the universe. 3 minutes after the explosion of the universe, these began to form. And then the next lightest thing, and there's a little bit of lithium that was formed then too, but lithium and almost all the other elements that we're familiar with came not from the Big Bang, but they came from stars that exploded. Either they dying stars or massive stars, supernova, and that sort of covers or exploding white dwarfs. But you'll notice that all the light elements were understood. And now here comes the new event. You find out all these things that are purple, that are violet, are regions that are very, very much higher mass, more neutrons. And now we know, which we didn't know before, we had guessed at this, that they are made in merging neutron stars. So for example, we now believe that all the gold and all the platinum and mercury, and well, some of the mercury is made in other sources, but all the gold and platinum, certainly, and all the heavies are made in neutron star collisions. And that was a piece of knowledge. We had guessed that, but now we know it better. And this was done through looking with optical and infrared and radio telescopes and UV telescopes at that dying ember of the neutron star collision. So that's a very fantastic thing that came out of it. Another thing that was fantastic, and that's looking to the future, is this picture, which is a little more difficult to explain. But what this is that you have an interesting thing that we didn't have before. By having a neutron star collision at a place in the sky where you know it, you know a lot about what's going on, because you can look from the waveform of the chirp, you can get the masses of the neutron star. From the masses of the neutron star, you put them back into the Einstein equations, solve for the strain at the source, and knowing that you can now get the distance to the source by just looking at your detector output and seeing how big it is. How big is the strain measured in your detector? If you have calculated, you can tell the distance quite well. And so you now have a very important thing. You know the distance to an object, and you now can then identify it with that galaxy that was out there. You know two things which are very, very important to the understanding the universe. The universe, as you probably know, is expanding uniformly with the velocity of the objects moving faster and faster, the more distant they are away from you. And here are two ways of measuring that by people with one way that was measured is the classical way of measurement is here's on this axis in these units of crazy, it's in velocity per distance, kilometers per second per megaparsec, which is just 3 million light years. But this is a group that does this. People do it by looking at supernova. They get that ratio. This is called the Hubble constant. It's got this sort of uncertainty. And here is the thing: if you solve the equations of the initial universe, which was done by the Planck satellite, the data from the Planck satellite and earlier data from WMAP, you get a number like this. They're not quite the same, but that's important, but not as important as the fact that you can, by just doing that one measurement with that neutron star, you can say this is a probability, how high is the probability of a particular value of the Hubble constant from that neutron star collision. And this is an accident that falls between this, but it shows you have another method now of doing cosmology, of measuring the universe by using gravitational waves with a known object out in the space. You can, in principle, actually solve all the cartography of the universe all over again. And that's something for the future. And it's going to be very important as time goes on. Here are less important things, but they haven't been done yet. Another thing that's going to be done, and this is the future, Kagra is going to be part of that, is you can learn something about how stiff the neutron stars are. In other words, here 2 neutron stars have been going, and you notice that one has distorted the other. They made it a little elliptical. And that fact that you have pulled a tide in the neutron star changes the waveform. It makes it go a little faster. That dotted waveform that's in here. That we're not yet at the signal to noise, and the number of these things that we've measured is still not good enough to get what's called the equation of state of nuclear matter. So that's something that's ahead of us. Here's another thing that's ahead of us. When the 2 neutron stars come together, they make a fluid of neutrons. And that fluid has oscillation frequencies. And here are some theoretical guesses of the oscillation frequencies. They're high frequencies. They're up in the kilohertz. And here are possible for different kinds of equations of state. You get different frequencies. And here are here is what the spectrum of such a waveform. And you can see it falls above the noise of the noise. This is the strain sensitivity of LIGO. It should fall above the noise of LIGO. And if we build something, which we'll talk about in a minute, it will really be seen. So this is something that's way ahead of us. We haven't anywhere got near to that, but we can now measure the equations of state of nuclear matter and also the fluid dynamics of what happens after you have a neutron star collision. So that's ahead of us. And here then is another example of what is ahead of us in a different way. This is sort of a picture like Professor Kajita showed something like this, but he didn't dwell on it. But let me dwell on it a little bit. This is a picture of the sensitivity in strain, in the spectrum of the strain versus frequency. So here, for example, is a strain of 10 to the minus 23 right up in here per hertz. That's a spectral density of strain. So if you multiply that by the square root of 100, you get 10 to the minus 22 RMS strain, which is sort of 10 times better than 10 to the minus 21. It's just well within, and this is the noise of the equivalent noise of LIGO now. If LIGO gets to design sensitivity, which it's not yet at, it needs more power and there's a little improvement at low frequency. This is just a design of advanced LIGO. We're working our way to getting to that. And here then is a thing that's being planned, is already in the works for the LIGO system now. It's called A+. And this is about as much as we're planning right now for what might go into LIGO. Kagra has similar plans. So in probably 2 or 3 years, we hope everybody will be sort of at a sensitivity down in here, which will be wonderful. Now, for the very distant future, let's say 10 years from now, there are ideas in Europe and ideas in the United States. I'm not so sure if there are ideas yet in Japan about this, but of building a system which is even much more sensitive. We call it the Cosmic Explorer. And that is a system that has about 10 times larger scale. The way you win in this, the noise doesn't change much as you increase the size of the system. But what grows is the signal grows with the length of this detector. So the idea is to make it not 4 kilometers, but 40 kilometers. And in Europe, they're thinking of making a triangle underground, 10 kilometers on its side. They're quite comparable in sensitivity. And here is sort of what such a detector might do. And that's a nice little picture. It shows a lot of stuff. This picture shows you that redshift is same as distance away from us. That's the redshift of the spectral lines. And here is the population. The white dots are the population of black hole pairs. And right now, if you are looking at that blue line, is going to be the sensitivity of the next run with LIGO. Okay, so we're not out very far. Whatever falls within that is what can be detected. What falls outside of it, you can't detect yet. But if you go to A+, for example, the green line here, you're going to pick up a lot more. And if you go to the Cosmic Explorers, which are the red and purple ones, you pick up every black hole pair that is in the universe, at least we believe. And then you're really doing cosmology. You're out looking at the entire universe. And you can then begin to ask questions like, are the black holes primeval? Do they come from the Big Bang, some of them? And that would be a fascinating question to answer. The same thing here goes on the left side. It's about binary neutron stars, and they're harder to see because they're lighter. And you can see that even if you make A+, you're still not out in the you'll get a few of them per year. They're in here. But as you go to, let's say, Cosmic Explorer 1, you begin to get to most of them. And if you go to Cosmic Explorer 2, which is a change in technology in that same system, you will make it possible to see all the neutron star pairs. This is just a nice way of describing what you get if you make a better detector. And here's my last slide. I want to quickly give you a feel for what is going on in the whole field. So this is a picture of frequency down here, going from, let's say, 10 kilohertz down to once per universe. And one way to look at it is up here is the time. This is time instead. Here's minutes, fractions of seconds, minutes, hours, age of the universe. And this is the strain level that's associated with detecting things. And here are the things that we are going on in the whole world at this moment. Cagra and LIGO and Virgo live out here in the 10 to minus 23, 10 to minus 24, 10 to minus 25 region, and the frequencies of around 10 hertz to about 10 kilohertz. And here are all the things that we see, these compact binary things. We already seen a lot of signals. They're going to be things which we haven't even thought about. So that, we can't put everything on that list because some of it we don't know. Another project that is also going on right now and has been going on almost as long as LIGO is something called LISA. That's the Laser Interferometer Space Antenna. And that's being done in Europe right now, but with some contribution from other countries all over the world. And was started in the United States, but the United States didn't have the money to really see it through. So what it is a triangle of spacecraft that go around the sun. There's the sun. They go around the sun at the radius of the Earth, and they get parked at the Lagrange point of the Earth and the sun. And that orbit is a very clever orbit. That equilateral triangle, it keeps itself. You don't need a lot of station keeping. And this hopes to fly by let's say 2030 something, 1, 2, 3, something like that. And it will see massive black hole collisions, like the ones of the black hole in our own galaxy. That's a million solar masses. That'll be huge signals. And it'll also see small mass black holes falling into large ones, which are very, very good for testing general relativity. And it'll see white dwarf stars in our own galaxy, many, many, many of them, making a background. So this is a very exciting project, and that is in the future. Here is one that's ongoing at the moment using pulsar timing. This is these pulsars, which are very good clocks, and you will look at them with radio telescopes in using different pulsars in our own galaxy. And if a gravitational wave comes sweeping through the galaxy, it'll cause the period of the pulsars to change. And so what you do is you look at the period of the pulsars against an atomic clock, and you look at the differences, slow differences, periods of a year, a couple of years to maybe a fraction of a year. And they may have seen something, they're not sure of it yet. And finally, the most exciting thing of all, I think, is something which is to look at the cosmic background radiation that comes from an epoch of the universe which is unbelievably short. It's called the inflationary period. And during a time when the universe went by something like 30 orders of magnitude in scale in less than 10 to the minus 30 seconds. An unbelievable, crazy time. It's a time when quantum theory determined the structure of the universe. And if there were quantum fluctuations in that very short time, they will make gravitational waves. And these gravitational waves are not easily detected by any of these detectors here. They're very much smaller. They're way below. They're down way below this picture. On the other hand, there is a possibility for seeing the effect of those gravitational waves on the electromagnetic cosmic background radiation, on the polarization of that radiation. And that's what people are looking for right now at the South Pole, in Chile, and it's called looking for the B modes. And that would be very exciting if they see something. So this is the future. Thank you very much.